Hello, Sararit.
Hello, sir. Good morning.
Good morning. Can you hear me well?
Yes, very well.
Okay, then let's start. Actually, when I turn on the camera, it's covering some space. That's why, I don't know, if you do not have discussion, I just prefer to keep it on. Okay. So if you can hear me well, let's continue. And we're going to have class for about 30 minutes. After that, we will have break, maybe 10 or 15 minutes. And we will have the second session. That is what we are going to do today. As you know, actually, we were talking about matrix algebra. It's about some properties of matrix operations. And we stopped here. We were talking about the transpose of a matrix. That's another operation on matrices. And from the definition, if you remember, how did you define the transpose of a matrix? Because, most of the time, the students or we people, when we don't understand the definition well, then we just get stuck when we are trying to prove something or trying to understand some fact here. So by the definition, actually, what is the definition of transpose? Actually, this transpose operation, right, it just actually transforms or changes the rows of matrix A into columns of, for example, let's say here we are given matrix A, right? If let's say this one is ij element of matrix A, when we just transpose this, we will have new matrix. That means it's just changing rows of this matrix into columns of this new matrix. That is, we will have here I, A, J, I, right? And also, if you remember from yesterday, if we have this kind of matrix, let's say A, B, C, D. If you transpose this, the rows of this matrix become the columns of this new matrix. And here we have A, B, and here we have C, D. Okay. So using the definition, this theorem says that let A and B be matrices. Here, two matrices whose sizes are such that the indicated operations can be performed. That means that actually here A plus B, I can add this, A times B, that means that we can multiply A by B, and let K be a scalar and a real number. Then the first property says that if you just transpose a matrix, and after that transpose one more time, it just gives us the original matrix back. Okay. And okay. The proofs are not so difficult. The second one says that A plus B transpose. If you're given two matrices and if you just add them and after the transpose, it is the same as transpose each matrix and after that add them. And we'll get the same result. And third one, if you're given matrix A and multiply by some kind of real number K and transpose this, it is the same thing as first transposing the matrix A and after that multiply by K. And this one actually, especially, you may get confused or it may not be so clear why A times B transpose equals B transpose and A transpose. Okay, so let's just start with A. Okay, so they'll get some idea. Okay, now assume that we are given matrix A. Okay, so if I transpose, let's say ij entry, I mean, if you transpose matrix A, we will have new matrix, right? That means that ij entry of this matrix, when it transpose, it becomes AJI, right? That means that's the definition of the transpose. As the rows becomes columns means this one is row, it becomes here column. This J actually represents the column, and it represents here row. So again, using actually the same definition here, if I just write one more step, how about AJI entry of this new matrix? If you transpose this, actually it will give us this element, that is IJ, right? JI transpose becomes IJ. Now from here, if I just write this together, AIJ entry, and I have to transpose this and the transpose one more time. this inner part we have just calculated here, that's equal to AJI. So here we have AJI, and here we have transpose. And the second one, we did this here, that's equal to AIJ. Actually, that is true for every possible value of I and J, right? When I equals 1 or 2, depending on the number of rows of this matrix A, number of columns of matrix A. So for every possible value of ij, that's true. So now if you just generalize this, then since it is true for every value of I and j, then A transpose, that's equal to just A. That is the proof of the first part. And how about B? Let me just do B here, since still we have space. How about maybe I can draw more. Okay, B. So A plus B transpose equals A transpose plus B transpose. Why? Again, if we just pick one entry of A, that is, let's say ij entry, and we are adding to ij entry of B, right? So we have to do, calculate this. Assume that when we just add these two things, actually we will have the sum, right? Let me just label this by Cij. Then here we will have Cij, and here we have transpose. And by the definition, Cij transpose, when it transposes this, it gives us this entry of new matrix, right? And equals, again, what is Cji? It is just equal to AJI plus BJI, right? Because the ij equals AIJ plus BIJ, that means CJI will be equal to AJI plus BJI. So that's equal to, actually from here, since it is true for every value of J and I or I and J, that means that we can conclude that then A plus B transpose is equal to A transpose plus B transpose. All right. That is the proof of B. How about C? It says that K times A transpose equals K times A transpose. So I can just do this here, C. Again, the same, using the same idea, I mean, just a definition, right? This K times A. I'm multiplying a matrix by a scalar. What does it mean? It means that we have to multiply every entry or every element of A by K. So if we just pick one entry of A, that is Aij entry. Okay, we have to transpose this, right? So let me just multiply this. We will get new value. Let's say it's equal to Cij. That K times Aij. I'm just labeling by Cij. And here we have transpose. So that is equal to Cji, right? And what is Cji? Cji also actually Ji element and multiplied by K. So that's equal to K times Aji, right? Because here every entry is multiplied by K. That means also new matrix Cji. Also here that entry is multiplied by this entry of A and by K. So which is equal to K times, what is Ji? Again, by using the definition of transpose, that's just equal to Aij transpose. So that's, again, it works for every value of I and J. Now we can conclude here that and K times A transpose, that's equal to K times A transpose. That means that if you're given matrix A, and if you just multiply by a constant and transpose this, it is the same as first transpose it, then multiply by K. It gives us the same result. And how about D? AB transpose equals B transpose A. I think I need more space for that. Okay, immediately I can just add one thing. Okay. So AB transpose equals B transpose times A transpose. Again, using the same similar idea, we are not taking the whole matrix, we just take one entry. Because again, by definition, Aij entry transpose is just equal to Aji. That's the definition of transpose actually, right? So again, using this, now we have to prove that, which one is it? D. Okay, that is D, right? We have to show that A, B transpose, all right. That's equal to B transpose and A transpose. All right. So again, by using definition, this AB transpose, let's just get only one entry. That is Ij entry. Okay. By the definition, actually, if you remember, how did it define the product of A times B? That's equal to, actually, let's say the product equals C. That means that Cij entry, right? Actually, that's just equal to row I of A. Actually, we should multiply this by column J of B, right? For example, let's say we are given matrix A times B. That's equal to, let's say here we have A, B, C, D, and here we have E, F, G, H, right? Now, if I want to write this entry, let's say here we have C11. What does it mean? We should multiply the first row by the first column, right? That is the row 1 by column Y. That gives us C11. If I want to get this element, for example, this element, right? That means I should multiply the second row by the second row column. Well, how about this one? 1, 2, the first row by the second column. In general, that's the definition of the product of two matrices. The Cij entry that equals row I of A dot column of J, B. And also by actually without this dot product, I can write this. But if I just don't write this one, this dot product, at the time it will be matrix multiplication. I cannot actually interchange these two things, right? That's why I prefer to use here dot product, because we know that for dot product, we have this property, A dot B is equal to B dot A. But if I just write this as a matrix product, I cannot actually write this A times B is not equal to B times A. And since actually it's just one row and one column, they look like exactly vectors, I prefer to use this dot product operation here. So by the definition, just imagine that here we have one matrix here, or the one entry of the product matrix here, Ij entry. What does it mean? It means that by actually the definition that is just what is it? A, B, right? A, B. What we have here, J, I. Because here we have transpose, right? And this Ij, it becomes here Ji. That's the definition of the transpose. That is equal to, again, by using the definition of this product, that means that that is row J, right? Because here we have the first index is J of A dot, and here we have column, here we have I of what we have here, B. Now, again, just using the definition of this transpose, that's why you should understand the definition very well. I mean, not actually how it looks like, but actually how we are writing using this index notations. So that is equal to, here we have row Ji. Instead of this one, how can I change this into column? And if I just write here transpose, right, the row of this matrix becomes columns of its transpose. So here I can just write as column J of A transpose times, and here this one row, and what is it? I of B transpose. Now I'm going to use this property of dot product. I can just interchange this, right? So that's equal to row, and here we have I, because I have to write this as Ij. That's what. Row I of B transpose dot column of J A transpose, which is equal to, exactly, actually, it is the definition of this one, row I, A, row I, something, and column J, B, and column J of something. I should just write here then, that is equal to B transpose, A transpose, and what we have here we have IJ. So here we have IJ. And this thing is true for every possible value of I and J. So now we can generalize that here, then A, B transpose is equal to B transpose and A transpose. Okay. And also actually we can generalize this thing in general. How about if we have three matrices then? And here we have A, B, C transpose. That's equal to C transpose, B transpose, and A transpose. Okay, good. And the last property, it says that AR transpose equal to A transpose R. I think it is not so difficult to see this because that is a E1, the last one. A transpose, is it A transpose? AR. A to the power, okay. A to the power of R transpose. And we know that the definition of power, right? This A to the power R means this matrix A is multiplied by itself R times. Here, of course, R is non-negative integer. So here we have A times dot, 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 and here we have A. How many A's here we have? We have R A's, and here we have transpose. And using this definition, that's equal to A transpose. Of course, I'm just writing this in reverse order. And A transpose dot, dot, dot. Here we have A transpose. How many A transpose we have? R, because here we have R A's. And again, by using the definition, here we have one matrix, another matrix, all are the same, and they are multiplied by itself R times. So I can just write it as, just right here, equals A transpose to the power of R. All right, gentlemen, anytime if you have a question, you can raise your hand. I think you know how to raise your hand in Zoom, right? You can stop and ask. If you don't ask anything, I will just keep talking. Next example. Given a matrix A whose entries are 2, 11, -5, and 6. And A transpose, what is A transpose? That means that we should just actually here, we know that this one is 2 by 2 matrix, and also the result will be 2 by 2, no problem. Now I should just write each row of A as a column of this A transpose, right? That is 2, 11, here we have 2, 11, -5, 6, and here we have -5, 6. And how about A plus A transpose? A plus A transpose, what is it? Here we have A plus A transpose. For B, A plus A transpose, what is A? A is 2, 11, and -5, and 6, right? Plus A transpose, we have just calculated here, that is 2, -5, and 11, and 6. So if you just add them up, 2 plus 2, that's equal to 4, and 11 plus -5, that's equal to 6, and -5 plus 11, that's equal to 6, and 6 plus 6 is equal to 12. Okay, so actually now soon I'm going to prove this as a theorem, or we're just going to give this as a theorem. What you have seen here is if you just add a matrix and to its transpose, what we notice here, the 6 and 6, they are exactly the same, right? They are equal. And what is it? If you just draw a line here, it is symmetric. These numbers are the same. So now you will see that if you add A to its transpose, always we obtain a symmetric matrix. So that is a symmetric matrix. And how about A times A transpose? Here we have A, that is A transpose. If you multiply them together, you know how to multiply two matrices. So we'll just multiply these things together. We got here 125, 56, 56, 61. Again, if we just draw a line here, what do you have here? These numbers are equal. That is symmetric above this line, above the diagonal. So again, actually in general, it is true. If you multiply a matrix by this transpose, So actually, it is symmetric matrix. And what we learn from here, when we are multiplying this, if you just write the diagonals and above the entries which are above the diagonal, so you don't have to compute the other entries. Immediately, you can just copy and paste here. Why? Because it's symmetric. All these entries are equal. And how about if the result is, for example, 3 by 3, or 5 by 5, or 4 by 4? So once you just write these entries, right? And also, you just write these entries here. So I should just copy this one and put here, and copy this and put here, copy this and paste here. So actually, we're just reducing the number of our computation here. Anyway, another example is A transpose times A. And if you just multiply this, we will get this answer. You know how to multiply these two things. A transpose, we already did here, and done here. And A is already given here. If you multiply them together, we get this answer. Again, if you notice here, actually it is, what is it? A symmetric matrix. So, after observing this, we'll just actually conclude this with a few. Before this, there's the one more example. Now here, we need to evaluate these things. Okay, we should do this manually. Let me use green. So B transpose, as you see here, what is B here? B is 2 by 3 matrix, right? So that means that here, B transpose, it will be 3 by 2. So I will have something like this, 3 rows, right? 1, 2, 3, 1, 2, 3. We will have this kind of matrix, right? And we know that the first row, it becomes the first column. So here we have 2, -1, and 3. And here we have 1, 0, and 5. And how about B plus B transpose? And B here, that is, as you see, B, here we have B, that is 2 by 3. And how about B transpose? That is 3 by 2. To be able to add two matrices, we know that they must have the same sizes or orders, right? And this one is 2 by 3, and this one is 3 by 2. So that means that that is not defined. This addition is not defined. That means that if you just add B to its transpose, it may not be possible. Even the previous one, A plus A transpose, if we have square matrices, right? And then we have symmetric matrix here. Otherwise, it's not possible actually if this B is not a square matrix and we cannot add it to its transpose. Why? Because here it's changing 2 by 3, 3 by 2. When actually it's possible if this 2 and 3, these numbers are equal. That means that B is a square matrix. And how about B times B transpose? Before we write the entry, the elements of the matrix, we have to actually make sure that it is possible, right? This multiplication is possible. Once again, what is actually the order of B? That is 2 by 3. And how about the order of B transpose? That is 3 by 2, right? And these are equal. That means it's possible. So we will get 2 by 2 matrix. It's good. So B transpose, that's equal to, what is B? B is 2, -1, and 3, and 1, 0, 5. And B transpose, that is 2, -1, and 3. And here we have 1, here we have 0, and here we have 5. Okay, and I know that I'm going to get 2 by 2 matrix here. All right, so if you multiply the first row by the first column, 2 times 2, it is 4, -1 times -1, it is 1, 3 times 3, it is 9, 9 plus 1, it is 10, 10 plus 4, so here we have 14. And how about the second row, 2 times 1, it is 2, -1, 0, and 3 times 5, 15, 15 plus 2, that is 17. Now, since we know that B times B transpose is always symmetric matrix, so I don't have to evaluate this entry, just write 17. And how about this one? It is 2, 2. I should multiply the second row by the second column. 1 times 1, it is 1, so it's a 0. 5 times 5, 25, so that is 26, right? Again, 17, it is a square matrix. So for this, it's always possible. How about B transpose B? B transpose, what is it? It is 3 by 2, and this one is 2 by 3. So we will get 3 by 3 matrix. B transpose is, here we have 2, -1, and 3, and here we have 1, 0, and 5. And how about matrix B? Here we have 2, -1, and 3, and here we have 1, 0, and 5. So here I will get a 3 by 3 matrix. 1, 2, 3, 1, 2, 3, 1, 2, 3. Okay. So to get this one, right, it's 1, 1. So I should multiply the first row by the first column. 2 times 2, 4. 1 times 1 is their sum is 5. And this one by the second column, 2 times -1. It is -2, it is 0. So here we have -2. And 2 times 3 is 6. 1 times 5, it is 5. 5 times 6, that is 11. And how about this 2 to entry? Because I know that the result is symmetric. So -2, this will be -2. This is 11, this will be 11, right? So how about this 2 to the second row by the second column, -1 times -1, it is 1. So here we have 1. And this one, 2, second row and third column, second row by third column, -1 times 3. It is -3, it is 0. So here we have -3. So that means that also this will be -3. We can check it. And the third 3 by 3, 3 element, that is C 3, 3. The third row by the third column, 3 times 3, 9, plus 5 times 5, 25. So that is 34. Okay, that is the advantage of knowing this property. Of course, we're going to use this more often in the future. So just to gain some, how to say, deeper intuition about these properties, how it works. So let's just conclude this section by this theorem, and we have just going to generalize what we have done a few minutes ago. So it says that if A is a square matrix, what does it mean? Square matrix means, so square matrix means, so its dimension is n by n, right? The number of rows of A is equal to the number of columns of A. So it says that A plus A transpose is a symmetric matrix. So symmetric matrix, again, this one is square matrix. For symmetric matrix, right? And what does it mean? We say that A is symmetric matrix if A transpose is equal to A. So to prove A, we have to show that the transpose of this matrix is equal to itself. Okay, so it's pretty easy. Here we have A plus A transpose, just using the definition. What happens if we take its transpose? If you transpose this matrix by using the definition, that's just equal to A transpose, because A plus B transpose equals A transpose plus B transpose. So here we have A transpose, and here we have transpose. That's equal to A transpose plus transpose, that's equal to A, and which is equal to A plus A transpose. So that means that it is symmetric. And how about part B? For any matrix A, A transpose and A transpose A are symmetric. So the first part, A transpose, again, using the definition to be symmetric, its transpose must be equal to itself. So using that property, again, property D, right, that's equal to A transpose, and here we have transpose times A transpose. And this thing is equal to A, and here we have A transpose. That means that it is, again, symmetric. And how about the second part? Here we have A transpose and A. So if you just transpose this matrix, here we have A transpose, right? The second one, times here we have A transpose and transpose, because A times B transpose equals B transpose times A transpose. So that is equal to A transpose here, A transpose, that's equal to A, right? So that means that also it is a symmetric matrix. Okay. All right, guys, let's finish this part with this quote, and because I will start the next section after the break. Too often we underestimate the power of a touch, a smile, a kind word, a listening ear, an honest compliment, or the smallest act of caring, all of which have the potential to turn a life around. That means that we should not actually be stingy, right, of using some polite words and saying good morning to somebody or hi, just showing your smile. It is really, really very important. And sometimes if people are very hopeless or very tired or very sad, just giving a smile may actually uh, give that person a big happiness or a big change in his life at that moment. Anyway, that is today's quote. Guys, have some rest. Okay, we have some time, but I don't want to start the next part here. So we will continue after 10 minutes. Bye.